Section 3.4 and 3.5 are general graphing techniques. There are some functions that are just so common in algebra that you need to know what they are when you first see them. You just need to have a quick mental image of what that graph looks like. If you go on to pre-calculus, you'll have a graphing calculator, and you can type in any function on that calculator and hit graph, and boom, there it is. But if you don't know what the graph is supposed to look like before you hit that graph button, every once in a while, either you make a typo or the calculator window is zoomed in so far that you can't see the whole graph. You'll get a bizarre answer. And if you don't know what the graph is supposed to look like, you won't know that it's bizarre. You'll just write it down. It's just like not knowing your multiplication tables. If you have to figure 3 times 4 and you accidentally put 3 plus 4 on the calculator and get 7, if you don't know your multiplication table, 7 might sound like a good answer to 3 times 4. The very same thing is true about graphing. Even though if you go any farther, you're going to have a graphing calculator, there are 8 basic graphs that you just need to know. And that's what we're working on today. You already know, or this semester we've already graphed linear functions. What does that mean? All right, first degree functions are linear functions, and when you graph a linear function, you get a straight line. So if x is to the first and y is to the first, it's a linear function and it's a straight line. These are other functions. The constant function, f of x is a constant. Actually, we've already talked about that one as well. And last week I said anytime you see f of x, you can put what in its place. What means the same thing? Yeah, that's just the y coordinate of an ordered pair. So for example, if you had y equals or f of x equals, it's the same thing. Any, miny, miny, mo, what about y equals 2? You already know what that graph looks like. What is it? It's a horizontal line. All right, so it's just a horizontal line through 2. The constant function, the graph of a constant function always is a horizontal line because f of x is the same thing as y, and we already know y equals a constant, it's a horizontal line. The linear function, f of x equals x, well, actually, that's the same thing as y equals x, and we've already graphed that. Specifically, I know that that equation is in what form of a linear equation? What's that form when you have the y by itself? That's slope-intercept form. I can just look at that and tell you the slope is what? 1. And the y-intercept is, there is no constant on the end. You could put a plus 0 if you wanted to. So the y-intercept is the origin. To graph that line, just start at the origin and count up 1 over 1. And there's the line. I think you either have 6 or 8 graphing problems on the test. I can't remember which. I think it's 6. One will be a linear function that's either in slope-intercept form or standard form. One may be y equals a constant, which is a horizontal line. One could be y equals a constant, or x equals a constant. What does x equals a constant look like? A vertical line, you could have one of those on the test, but why will you not have a vertical line in a section that says graphing functions? Because what? Why is it not a function? That line has one x that has infinitely many y's. All the ordered pairs on that line have the same x, but a different y. So it fails the vertical line test. It is a vertical line. So you could have, I could say graph this equation or graph this relation, but on this problem I couldn't say graph the function because it's not a function. All right, going on to some things we haven't graphed so far. F of x equals x squared or just y equals x squared. We're going to talk a lot more about the square function in chapter 4, but that's after spring break. Right now, all you need to be able to do is, if you don't know what it looks like already, make a tiny little XY chart. What we're trying to do is get you away from needing to make an XY chart, but it's always your fallback method. When all else fails, when your memory fails due to panic on a test, you can always make an XY chart. So if I let x be eeny, meeny, miny, mo, is there anything I cannot let x be in this function? What's the domain of y equals x squared? What can I let x be? Anything. I can square anything in the whole wide world. So I can let x be anything, not being very creative this morning. I'll just pick -2, -1, 0, 1, and 2. Now, if I'm graphing a line, I really only need 2 points because between any 2 points in the whole wide world, you can draw a line. How do I know this is not going to be a line? It's not first degree, so I picked a few more points just to make sure I have a good idea of what this function looks like. If I let x be -2, then -2 squared is 4. Let x be -1, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Does the fact that I have these two different x's that give me the same y, does that mean this is not a function? No, that's not the problem. Two different x's that give you the same y is not a problem. That is a function, and if you graph those 5 ordered pairs, you'll see what it looks like. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. It's this nice, smooth, U-shaped graph, which you may remember from somewhere else, some other math class. What's the name of that nice, smooth, U-shaped function? That's a parabola. All right. If you remember that, yay. You don't have to remember it for test 2. We'll talk more about parabolas in chapter 4. But for right now, if you have a nice, smooth, U-shaped graph with its turning point at 0, 0. By the way, one other bonus word here. What do you call the turning point of a parabola? It's vertex, all right? So if you have a nice U-shaped curve with its vertex at 0, 0, that's all I'm looking for. If you need to be any more specific than that, then you can graph it on a graphing calculator in pre-cal. All right, D, the square root function. What's the domain of this function? You can't let x be negative numbers here because you can't take the square root of a negative without exiting the realm of real numbers. So you said any, did you just say any positive number? What can you include other than positive numbers? 0 or any positive number. Almost, but you can include 0, and how do you show including in interval notation? No, a bracket on 0. Yeah, a bracket on 0 because you can take the square root of 0 as long as it's not in the denominator.
So pretty much what you're saying is you need to go left any bracket, you know, to get as far as you can go back.
Yeah, it's like a stop sign. Don't go to the left of 0. All right. I don't know what this is going to look like, so I'm going to make an XY chart. I just needed to know the domain to know where this graph stops. There is no graph to the left of 0. 0 is the smallest thing I can let x be, And since I'm going to have to take the square root of x, I'm just going to pick x to be my first few perfect squares, things I can take the square root of in my head. The square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. Graph those three ordered pairs. Notice that if I just graph the first two, I might think, hey, this is a line. I can put a line through 0, 0, 1, 1. How do you know it's not a line? I'm talking about just looking at the equation. How do you know it's not a line? It's not linear. It's not first degree. How could you write square root of x with an exponent? X to the 1/2? So it's not first degree, therefore it's not a line. And if you graph this third point, you can see that it's not a line. It's a curve. As a matter of fact, it's a half of a sideways parabola. You don't have to be able to say that. You just need to know what the general shape of the square root function looks like. All right, the cube function. Say like I don't have any idea what it looks like. Make an XY chart. What kind of x's can you cube? What's the domain of this function? You can cube anything in the whole wide world, negative, 0, or positive. So the domain of this function is negative infinity to infinity. You can pick x and y to be anything you want to. I'm going to make a horizontal xy table here just because I don't have room for a vertical. And I'm going to let x be, let's see, since I don't have any idea what this is going to look like, I better choose several points. Let's let x be negative 2, negative 1, 0, 1, and 2. And just cube each of those. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So what does this look like? Negative 2, 8, negative 1, negative 1, 0, 0, 1, 1. Ooh, look, if I only graphed those 3 points, I could put a straight line through them. I could think that that was a straight line, but I know it's not because this is not a linear function. 1, 1, and 2, 8. It's going to be up here somewhere. When you cube positive numbers, they get big really fast. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, then 125, then 216. They get big fast. That's why the left-hand side of this, that's right-hand side, the right-hand side of that graph takes off so steeply. And when you cube negative numbers, they get big very fast in a negative direction, which means they get small very fast. And that's the graph of the cube function. All right, what about the cube root function? What can you let x be? You can take cube root of anything. You can take cube root of negative numbers. What's the cube root of negative 8? Negative 2. So the domain of the cube function is all real numbers again, or negative infinity to infinity. And since I don't know what it's going to look like, I'm going to make an XY chart, and I think I better make it horizontal again. I'm going to try to make life easy on myself and choose x's that are perfect cubes so I can take the cube root of them in my head. What about negative 8 is a perfect cube, negative 1, 0, 1, and 8. All of those are perfect cubes. Cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. Those numbers look very familiar. Where have I seen those same numbers this morning? On the E part, all of the numbers were the same. The X's and Y's are just reversed. These Y's are the same as these X's. These X's are the same as these Y's. When you graph that cube function, I may have said cube function, I meant cube root function. When you graph that cube root function, it looks just like the cube function, except for what? Turn sideways. Now that I think about it, kind of the same thing happened when I graphed x squared and square root of x. This is a parabola. This is half of a sideways parabola. Now, it's only a half of a sideways parabola because y equals the positive square root of x. If I wanted the bottom half of that parabola, what could I change about that equation? Put a negative in front of the square root, and then I'd get the bottom half of the parabola. But if I have both halves of it, it's not a function because it doesn't pass the vertical line test. So this looks like that turned sideways. This looks like that turned sideways. As a matter of fact, two functions which have the same ordered pairs with the x's and y's switched are called inverses of each other. They undo each other. Squaring and square rooting undo each other. Cubing, taking the cube root, undo each other. So they're called inverses of each other, and anytime you graph a function and its inverse, the graphs are a reflection about the line y equals x. That's more than you have to know. If it's not typed, you don't have to know it. But if you go on to pre-calculus, we'll have a section on inverse functions, and you'll go, oh, that's what you were talking about that day, that cold, cold day in March. All right, two more. The absolute value function. F of x equals the absolute value of x. Well, that's the same as y equals absolute value of x. And since I don't have any idea what that looks like, I'm going to make an XY chart. What's the domain of that function? What can I take the absolute value of? Anything in the whole wide world, you give me a number, I can take its absolute value. So I don't have to be careful of what I let x be. I can pick the same x as I did for the cube function. Negative 2, negative 1, 0, 1, and 2. The absolute value of negative 2 is what? 2. Absolute value of negative 1 is 1. Absolute value of 0 is 0. Absolute value of 1 is, oh, absolute value doesn't mean opposite. Absolute value means the distance a number is from 0 on a number line, and since it's a distance, it's always positive. 1 is 1 unit from 0 on the number line. 2 is 2 units from 0 on a number line. Hey, there's 2 different x's that gave me the same y. Is that going to be a function? That's not a problem. Two different x's that give me the same y is not a problem. So let's graph those 5 ordered pairs. It looks, before I connect the dots, it looks a lot like this squaring function. I could connect those in a fairly smooth U-shaped graph, but here's how I know it's not a U-shaped graph. As a matter of fact, this is a V-shaped graph. I'm going to go ahead and put it in there, and then I'll tell you why. That's a V-shaped graph because of the definition of absolute value. Think of how I could define absolute value. If I put in any positive number, what does the absolute value function spit out? The same thing, right? So for any positive x, anything greater than or even equal to 0, if I put anything greater than or equal to 0, the absolute value gives me the same function, y equals x. But if I put in a negative, what does the absolute value function spit out? The positive version, or the positive of whatever I put in, the opposite of whatever I put in. If I put in a negative, the absolute value function shoots out its opposite. Now, we have not talked about this yet, but this is called a piecewise function because it's defined to be one thing for part of its domain and something else for another part of its domain. Y equals x is the right half of this V-shaped. Y equals negative x is the left half of that V-shaped. It's two half lines that join. That's how I know it's a V. They join at a point rather than a smooth U-shaped curve. Now, if you totally get that, yay, I'm so happy. If you don't totally get that, then for the next, what's today? Monday? For the next 2 days, you need to have each function on an index card with its graph on the back and be flipping those index cards to yourself at all the red lights you stop at in the next 2 days. All right? You just need to know when you see y equals absolute value of x, that's V-shaped. Now, on the test, if you give me a V shape, but you have it in the wrong place, and we'll talk about that in a minute, I'll still give you partial credit because you knew that it was V-shaped, you just got it in the wrong place. If I give you y equals absolute value of x and you draw a circle, that is worth no points. There is nothing I can do. If you don't even have the shape right, then it's -5. So I know that 8 functions, you could put them on 8 index cards and memorize those by Wednesday with no problem. Last one, the reciprocal function, also known as the flipper. It takes any number you put in and flips it, because that's what taking the reciprocal does. What's the domain of this function? Anything but 0. I can flip positives and I can flip negatives. I just can't flip 0 because that would give me 0 in the denominator. I'm just going to write the domain this way. X can be anything but 0. Now, for reasons you may not understand for just a jiffy, I'm going to carefully pick my x's here. I'm going to let x be -2, -1, but also -1 half and -1/4. I'm going to put 0 on my chart just to help me remember that if I let x be 0, what is this expression? Not 0, undefined. And then I'm going to choose some positives. What about 1/4, 1/2, 1, and 2? I had to pick a lot of x's here because I have no idea what this is going to look like. If I let x be -2, what is the reciprocal of -2? No, -2 is -2/1. If I flip it, it's -1/2. What's the reciprocal of -1? It's still -1. -1/1, if you flip it, is still -1/1, or -1/1. What's the reciprocal of -1/2? -2. And the reciprocal of -1/4? -4. And then when x is 0, the function's undefined. When x is 1/4, y would be 4. When x is 1/2, y would be 2. When x is 1, y would be 1. And when x is 2, y would be 1/2. All right. Let's graph those 8 ordered pairs. -2, -1/2 is darn close to the x-axis. -1, -1, -1/2, -2, -1/4, -4. Now it's getting so close to the y-axis, it's hard to even plot the point without being on the y-axis. When x is 1/4, y is 4, 1/2, y is 2. When x is 1, y is 1. When x is 2, y is 1/2. And I have all my plots pointed, but I don't know how to connect the dots there. 0? Yeah, because I can't graph undefined. Put a dot on 0, undefined. Think about as my x's keep getting bigger and bigger here, and I take the reciprocal. Take the reciprocal of 1 is 1, and then the reciprocal of 2 is 1/2, and then 1/3, 1/4, 1/5, 1/6, 1/10, 1/1000th, 1/1,000,000th. What's that getting closer and closer to? 0. As your x's get infinitely big, your y's keep getting closer and closer to 0. Are they ever going to be 0? No, there's nothing you can take the reciprocal of and get 0. So this piece of the graph is just going to keep getting closer and closer to the x-axis as your x's get infinitely big. What about as your x's get close to 0? The reciprocal of 1/2 is 2. The reciprocal of 1/4 is 4. Then I'm going to have the reciprocal of 1/5 is 5, and then 10, and then 1,000,000. As my x's get closer and closer to 0, my y's are taken off to infinity. The reciprocal of 1/1000th would be 1,000, way up there. So that's what the right-hand side of the graph looks like. The left-hand side looks like it's going to be the mirror image of that. As I keep taking the reciprocal of numbers that are more and more negative or infinitely small, my y's are going to get closer and closer to 0. And as my x's get closer and closer to 0, my y's are going to take off to negative infinity. How do I know I'm not supposed to connect these somehow? Why wouldn't these two pieces of a graph be connected? To connect them, you would have to cross the y-axis And what do all the points on the y-axis have in common? Well, the points on the y-axis, what's true about all of the x's on the y-axis? They're 0, and you just told me I can't let x be 0. So this graph cannot be connected. It can't cross the y-axis, or that would be the same as letting x be 0. Once again, if you understand that, yay. If you don't, what's the closest tattoo parlor? That one downtown, I don't remember the name of it. Mothang's? Go to Mothang's and get this tattooed on the back of your eyelid before Wednesday. Or a less painful version, get you 8 index cards and memorize what the graph of the reciprocal function looks like, along with these other 7 functions. I don't think there's a person in here that can't memorize 7 graphs and at least get partial credit on these 6 problems on the test. You can know what these shapes are. And you have to, regardless of whether any other math course you take is going to allow you to use a graphing calculator or not, you still need to know these 8 basic shapes. All right. A minute ago, I said if you have the right shape, but you have it in the wrong place, I'll give you partial credit. Let's talk about what could move these graphs around, left, right, up or down, or even flip them upside down. Those are called transformations of the graph. By the way, these 8 basic graphs are in 3.4, and then the transformations are in 3.5. What moves them left, right, up, and down? Well, first, let's talk about what moves them left and right. That's called a horizontal shift. If I have y equals some function, it could be the squaring function, the absolute value function, the cube root function, any one of the 8 functions that we've talked about. If I add or subtract something to or from x before I take the absolute value, or before I square, or before I cube root, whatever it is that I'm going to do, if I add or subtract something before applying the function, that's a horizontal shift. And you may as well go ahead and hypnotize yourself. That horizontal shift always works the opposite of what you might expect. I'll show you why. This first example, y equals x minus 2 squared. If that was just y equals x squared, what would the shape of that graph be? It's a parabola. It still is a parabola, even with that minus 2 there. So if you graph a parabola, yeah, you get 2 points. But you have to have that parabola in the correct place. This parabola had a vertex of 0, 0. This minus 2 in parentheses moves the whole parabola the opposite of what you might have guessed. You might have said subtracting 2 would move it to the left 2, but go ahead and just know that subtracting actually moves it to the right. So one way to think of it is this critical number, the critical number of that function, or the critical point of that function, which for the quadratic equation is its vertex, is 2. It's always going to be whatever makes inside the absolute value, or squaring, or square rooting. It's always whatever makes that inside become 0. So the critical number is 2 because that's what causes inside the parentheses to be 0. If you have that problem on the test and you draw a parabola whose vertex is scooted 2 units to the right, we're not going for a great deal of precision here. That would be good enough. No, we will talk about parabolas more in depth next chapter, and then I'll ask for some more specific stuff. Right now, we're going for quick mental image. Example 2, y equals the absolute value of x plus 1. As soon as I see y equals absolute value of x, I think I know what that shape is. What is it? A V shape. And what is that adding 1 inside the absolute value do to the graph? Moves it horizontally, probably the opposite of what you would expect. It moves it to the left 1 unit. That means its critical number is -1, the opposite of the guy in the absolute value. No. Yes. And it will work for the rest of your life. The horizontal shift is going to be the guy added or subtracted in parentheses, moved the opposite of what you would expect. Adding actually moves it to the right, or excuse me, adding moves it to the left, subtracting moves it to the right. And that's all you need to know about horizontal shift. It's what's added or subtracted inside the parentheses, the absolute value, the radical, whatever the function does. So what about vertical shifts? Vertical shifts come from adding or subtracting something after the function is applied. If I just had on this first example y equals square root of x, I would know it looks like what? Half of a sideways parabola. Now, is this 3 added before you take the square root of x or after? After. It's not under the radical. If I said evaluate this for x equals 1, you'd take the square root of 1 and then you would add 3. It's outside the absolute or outside the radical. That's what makes it the vertical shift. The critical number is still whatever's added or subtracted under the radical. If there's nothing added or subtracted under the radical, the critical number is still 0. This graph isn't shifted left or right, it's just shifted up 3. So you look back here at the square root function, and you imagine this graph shifted up 3 units. And correct. Instead of the vertex, or not vertex, but instead of the leftmost point being 0, 0, if you shifted that up 3, where would that point be? 0, 3. And then just attach the same sideways half parabola. The horizontal shift works the opposite of what you would expect, but the vertical shift, adding does move it up, subtracting does move it down. And if you forget everything I said today, then on the test Wednesday, you could still do what? Make a little XY chart. You might not finish the test because that takes longer. So don't do that. X squared minus 4. Without that minus 4, I'd look at it and say, hey, where's my finger? There it is. It's a parabola. Is that, if I said evaluate this for x equals 1, would you square the 1 before or after subtracting 4? You'd square before subtracting. That minus 4 is subtracted after the squaring, which means it's a vertical shift. And that vertical shift works like I expect it to. Subtracting actually moves that parabola down 4. So all that I'm looking for is this point at -4, 0, and a parabola going through it, turning around at that point, 0, -4. That's all there is to vertical shifts. The only other thing we're going to talk about is a reflection about the y-axis, otherwise known as flipping the graph upside down. This example, if I covered up that negative, you'd say, well, what shape is it? A V shape, concave up V shape. Does it have a horizontal or vertical shift? Nothing's added or subtracted inside the absolute value. Nothing's added or subtracted outside the absolute value. So it hasn't been shifted. But if I were to make this XY chart for negative absolute value of X, I would just take the opposite of all those Y's, and when I graphed them, I'd have a concave down V shape. That negative just causes a reflection about the x-axis, or flipping the graph over the x-axis. What about negative x cubed? You remember what x cubed looks like? It's I don't have a good name for it. It's kind of snake shaped. Goes up from left to right. If I reflected that with respect to the x-axis, what would change about that snake? Going left to right, it would be going downhill instead of uphill. You probably didn't know that unless you read my mind. What the answer to what I was trying to ask. The snake's going to be going downhill. And without a horizontal or vertical translation, get this, its belly button is still going to be at the origin. Aw, belt snakes don't have belly buttons. I've had biology. All right. What about all of this put together? Can we look at a graph that has been shifted, or look at an equation that has a horizontal shift, a vertical shift, and possibly a reflection, and graph it without having to make a big XY chart? That's the goal. And again, you can't assess your competency at this section just by your ability to choose a multiple choice graph in the homework tonight. So do some problems that aren't multiple choice. I've listed some you can do from the book, and if you didn't buy a hard copy of the book, you can access it in the ebook, and that extra practice test that I gave you will give you an opportunity to do some graphing that's not multiple choice. But let's see how many of these we can do from page 253 in the time that we have left. Here's page 253. And I'm just going to put the first 18 problems up here are still multiple choice. Don't try to copy this down in your notes or anything. We'll have some others you can put in your notes. But let's just look at this matching. Yeah, matching, not multiple choice. These 6 problems that I'm showing right now, all of those are parabolas. So I know that all of those come from equations with what in them? An x squared. And these 6 are all V-shaped, so I know they come from equations with absolute value. Let's talk about the absolute value ones. Number 9 is an upside down V-shaped. What does that mean that I know about the equation? And what does that mean about the equation? It has a negative in front of the absolute value. That's what flips it upside down. What shifts it to the left? Positive 2 inside the absolute value, because that horizontal shift works the opposite of what you expect. So which of these 6 equations is it? L. The negative flips it upside down. No, it's not L. H flips it upside down and shifts it 2 to the left. Yes. Now, what we didn't talk about is stretching and compressing. What I know about this graph that you don't have to know is this 2 in front of the absolute value makes the graph more narrow. But I'm not going to check how wide your graph is. If you just had an upside down V shape, and in the L part, its turning point was 0, 0, that would be good enough. I'm sorry, what? Because it's more narrow? Yes. Okay. What about 10? It's an upside down V shape, so it also has a negative coefficient. but the V has been shifted up 2 units. Which letter is it? D. Negative makes it upside down. The plus 2 on the end shifts it up 2. So 18 is D. What about, Why did I say 13? I have no idea. Yes, 10 would be D. What about 14, a right side up V shape that's been shifted up 2 units? Which letter would that be? G? G, that would be to the right 2. C would be up 2. Vertical shift is what's outside, what's added or subtracted after the absolute value is taken. So 14 would be C. 17, right side up, V shape, shifted 2 to the right. That's G. Opposite of the guy in parentheses or absolute value or whatever you have, that's your horizontal shift. And then 11, V-shaped, that hasn't been shifted left, right, up, or down. That's K, and I don't care about you knowing this, but this is more narrow because of that 2 in front of the absolute value. If you can do the matching, yay. What's important is that you be able to do these graphs. So let me show you how quickly you're going to be able to graph after just a little bit of home practice. This is page 253 if you look it up sometime. And we're going to see how many evens we can graph in 20 minutes. I think we'll run out of graphs in 20 minutes. We're going to do this fast. Number 40. You can write f of x equals blah, 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 or I'm just going to go ahead and write y equals, because they're interchangeable. Y equals x squared plus 4. What does y equals x squared look like? It's a parabola, concave up, and what is that adding 4 after the squaring due to that parabola? Is it a horizontal or vertical shift? After the squaring is vertical, and vertical works like I expect it to. Adding moves it up 4. So that's the mental image that I have in my head. And then what I would put on the test is that. If you have a concave up parabola, you have 2 points. If its vertex is 0, 4, you have 5 points. The easiest 5 points you'll ever get in your life. Number 42. What does x cubed look like? Don't have a very good name for it. Kind of snake shape, going uphill, whatever you want to call it. It looks like that. And is that 1 being subtracted after the x cubed a horizontal shift or a vertical shift? Vertical, and specifically how? Down 1. So instead of, biologists, forgive me here, instead of its belly button being at 0, 0, it's where? 0, negative 1. I get some crazy looking graphs for this one on the test. That's supposed to be relatively smooth snake shape. It is not. Lord, what do I see on the test? It's crazy. It's not that. I don't know what that is. I'm afraid of it. Yeah, it's not that. All right. 44. What does y equals the square root of x look like? Square root of x? That half a sideways parabola that normally starts at the origin because 0 is the smallest thing you can take the square root of. Now that 1 is under the radical. It's added to x before I take the square root. Does that mean it's a horizontal shift or a vertical shift? Horizontal, and specifically that horizontal shift's the opposite of what I expect, so this graph moves left 1. Or if you just think about it, what's the smallest thing you can let x be in this function? It's not the smallest thing. It could be 1. It could be 0. What's the smallest thing it could be? Negative 1 would give me square root of 0, and that's the smallest thing I can take the square root of. That's why this half parabola is scooted 1 to the left, because negative 1 is the smallest thing that I can let x be. If you have a half parabola, that's 2 points. If its starting point is negative 1, 0, that's 5 points. If you have a circle, that's me coming to your house on spring break and roughing you up. What does y equals x cubed look like? It's okay if you have to look back because you haven't gotten your tattoo yet. It's that vertical snake. Sideways is cube root of x. But it's that snake going uphill from left to right. What does that 2 added inside the parentheses do to the graph? Moves it 2 to the left. It's a horizontal shift, and the horizontal shift always works the opposite of what you might have guessed. What does that 3 on the end of the equation do? Shifts it down 3. That's your vertical shift, and it works more the way you would expect it to. We're at 1,000 bonus points. Where is the snake's belly button? I'm embarrassed to have that on film. Huh? Yeah. It was at 0, 0, but it's been shifted 2 to the left and down 3. So here's what I'll be looking for. Because that horizontal shift always works the opposite of what we expect. Right here, adding 1 actually moved the graph to the left 1. Adding 2 moved the graph to the left 2. Okay? 48, I don't want to do. What about 50? 48 is just not interesting. What does y equals the square root of x look like? Half a parabola. Did you say half line, half parabola? Oh, I was thinking that was some figure from the Greek mythology. Half a line, half parabola. Man, I need to write that story. I'll think about it. It's a half a sideways parabola. What does that negative coefficient do to it? Upside down. Instead of being this, play like it didn't get wobbly on the end. Instead of being that, it's that upside down, or the bottom half of a sideways parabola. Hasn't been shifted left, right, up, or down because there's nothing added or subtracted under the radical, nothing added or subtracted outside the radical. 52. What does y equals x squared look like? A parabola. You don't have to know this, but that 3 actually makes it a little bit more narrow than your standard parabola. How does that subtracting 2 inside the parentheses affect the graph? To the right 2, that's your horizontal shift, and the horizontal shift's always the opposite of the guy in parentheses. And what does the adding 1 on the end do to the graph? So this vertex, which normally would have been at 0, 0, is now where?
2.
Over 2, up 1, right there. That's as good a mental image as you will need if you're going on to pre-calculus and you use a graphing calculator, because if it doesn't turn out to be a concave up parabola with vertex at positive 2, 1, you know that you've either mispunched something on your calculator, or the last person who used the calculator may have been really zoomed in on something. What if your calculator only showed you that much of the graph? I might think that, hey, it's a line, because that little piece looks like a line. But it's not a linear equation, so I know it's not a line. I would hit the zoom out until I could see the whole parabola. Or not the whole parabola, because it goes forever up, but the important parts. All right, 54. What's the shape? It's a V shape. What's the horizontal shift? To the left 1. And what's the vertical shift? Down 3. So instead of the vertex being at 0, 0, it's where? Down 1. Or excuse me, to the left 1, down 3. Vertex is at -1, -3. All right. I don't care about 56, 58. Correct. Actually, that's about all the interesting ones, 39 to 53. I'm going to make this one up, and it'll be our last one. I'm going to do everything crazy I can think of to it. Ooh, that's not what I meant. Do that one, and then I'm going to give you one more. Do that one super fast. Oh. There's our last 2. The first one is what basic shape? Snake. What does the negative do? Going downhill. Downhill snake with turning point where? -2, +1. Here's the basic shape. The negative flips it with respect to the x-axis. The adding 2 moves it to the left 2, and the adding 1 moves it up 1. And you don't have to write all that down on the test. I'm just trying to give you something to think about in your notes. That's all you have to put on the test. The last one, the one I meant to make up here, how does cube root of x differ from x cubed? Graph. It's the sideways snake, just like square root of x is the sideways parabola. So this is this horizontal snake, which is normally going like that. Can you see? Where's my graph? Can you see how that graph would be going if you flipped it with respect to the x-axis? Instead of being in the 4th and 1st quadrants, if you flipped it with respect to the x-axis, where would it be? Well, it's in the, I said the wrong thing there. I said 1st and 4th. I meant instead of being in the 1st and 3rd, it would be in the 2nd and 4th quadrants. So it's going to go like that instead because of the negative. And then what's the horizontal shift? To the right, 2. And the vertical shift, down 1. Do your best to make it look like a horizontal snake that is sober. That won't get you much on the test. Huh? Oh, is it not? To the right, 2 down. Oh, shoot. Yes, it should be this instead of what I drew. Ah! I had to mess up once. I wouldn't be myself if I didn't. There you go. Now,